What up, guys? So for this one, another Navier Stokes problem is two viscous incompressible emitted fluids flow steady down an infinite inclined plane, no velocity perpendicular to the plane. Both fluids, they have the same density, but they have different dynamic viscosity, or just viscosities, right? Air resistance is negligible, so that the shearing stress at the surface is zero, right? So at the very top, where that dark blue meets the white, um, shear stress is zero, and that's going to help us when we start doing the boundary conditions. We need to get the velocity profile U for both fluids at the interface, so at y is equal to 0, and the velocity at the top, at the free surface at y is equal to h. We also need to get the shear stress at the interface between them at y is equal to 0. So in my problem, I chose the datum right at the center, y is equal to 0, and then you have y is equal positive h and negative h for your boundary condition. So let's go ahead and get started, guys. All right, this one's no different than the other one, just that the surface is now inclined. In this case, I'm going to get the velocity and the shear stress at y is equal to 0, which I'm going to set right here. And then at y is equal to h at the top of the free surface, okay? So you could do from 0 to h to 2h. In this case, I do 0, h, negative h. Okay, it doesn't really matter because the only thing that changes is your general solution. But at the end of the day, your velocity profile should stay the same as long as you got the correct answer. And I'll tell you where it kind of like just changes direction. But the first few steps deriving that reduced Navier Stokes equation should be the same, regardless of where you choose the datum. That only comes at the boundary condition. So, right, just like all the other problems, we're going to start off with the equation itself. So this is in the x direction, right? This is your coordinate system. You want to tilt it. You don't want to keep it at the traditional xy, because then you're going to have two components for g, right? Because g is the gravity of the fluid, and it's pointing straight down. If you do that, I'm sorry, my bad, you won't have two, you'll have one. But the thing is, you'll have to modify both the x component and the y component of the Navier Stokes equations. It's better to just tilt it and get that g sine theta, and you'll see how we get it. But it's better to just get the theta of that gravity, if that makes sense, okay? But it's better to just tilt your axis. That way we only deal with the x component. So I just used it. This is from the book, right? I like to divide density to everything. So this is the equation you'll get if you do. If you saw the other videos, you know what I'm talking about. And once you get to this point, it's real easy. You just have to know what terms to cross out. It looks complicated, right? But you'll see it really is just straightforward. So that's step number 2, right? And if you've seen the other videos, you know what I do here. So you could kind of go ahead and skip it, right? But in this case, a steady state, so this term goes away, right? Anything related to time goes away. In this case, it's just this one, so we're good. There's flow only in the x direction. So you have the y flow, which is v, and w, which is z. Y and z, they're both 0, right? We only have flow in the x direction. So just because of that, these two are 0. So anytime you do like a partial v with respect to anything, it's going to be 0, right? Because take the derivative of 0, you're going to get 0. But this term cancels out, right? That v and that w. So just like that, we're left with this term on this side of the equation, okay? And then we still have all this. Free surface, so there's no pressure in the x direction. That's an assumption you should know, right, when you're exposed to the free surface. So that is 0. Gx, and don't get me wrong, if you were doing it in the y direction, delta p over delta y would not be 0, okay? This is along the x direction. There's no pressure pushing the fluid. It's just kind of flowing, if that makes sense, because it's exposed to the free surface. That kind of takes time to think about, so just FYI. But in this case, you're exposed to the free surface, so that's 0. It's infinite plates, right? So it's an infinite surface going in, okay? So that's what I drew here. Going in, the velocity profile is not going to change. I don't know if this is the velocity profile. I'm just kind of using intuition, right? Velocity is very high here, and then it just reduces until you get to 0 because of no slip up against the wall. So that's what I think the velocity is going to look like. But what I'm trying to tell you with this diagram is going into the page, it's the same profile regardless of where you're at. Okay, so that's what that means, infinite. delta U, right, the velocity in the x direction with respect to z, the change in it, right, is going to be 0. So that square, take the next derivative, that's just going to be another 0, right? So just like that, this term goes away and this term goes away. But this term had already gone away because of W, so we didn't really gain much there. And then look at gravity now. So gravity's pointing straight down. That's what I have here, G, right? Originally, this was my traditional XY, straight up and straight to the right? Positive X, positive Y. But because that angle tilted, right? I guess what I'm trying to say is, look at my 2 pencils. It was like this, but that angle, look at the straight bottom line, it went this way. So now that angle is theta, right? That's the same angle. That's from trigonometry. So that means this angle is also theta. And we want this component of velocity. So what is it? It's just G sine theta. It's this one right here. I just drew it over here, but it's that one right here. G sine theta, okay? So that's what our G of X is. It's positive because it's going in the positive X direction. Something to keep in mind. And just like that, we eliminated this one, we still have these two, we have this one, and we have this one, okay? So now using the laws of mass conservation for an incompressible fluid, I haven't been saying that in the other video, because this is true for an incompressible fluid. Within these partial derivatives, you have density, and that's assuming it is compressible, right? So, but in this case, it's incompressible, so you could just factor out the density and divide both sides by rho, and it just goes away. This is the mass conservation law. We know the velocity in the y and z direction are 0. So that means when you take the partials with respect to y for this term and with respect to z for this term, we're just going to get 0. So that means these two are 0. So that means this is equal to 0. That's what I have here. And take the second partial with respect to x, you just have 0 again, right? So that means this term goes away, and that means that term goes away. So now we're stuck with this term and this times this, okay? So now that I have that, this is my reduced Navier Stokes equation. It's just G sine theta, right? Your G of X plus nu times second partial of u with respect to y, okay? Now I'm gonna go ahead and throw this back in there, right? Make that substitution. I previously did it from here. It's just because this is the way I like to work. In this case, I'm going back to it, right? That mu right there, I'm gonna switch it back to nu. So what I did was I moved this to the other side, negative G sine theta. Then I divided it by mu over density, which is just this right here. So check it out. This is the general solution, right? I just moved this over. I moved this over here, so it became a negative. Rho G sine theta was G sine theta, but this became mu over density, so the density goes up top. And mu1 sine theta, that's it. So then what we do is we integrate it with respect to y, and you'll get the partial u1, partial y, and it's partial u1 because there's two fluids, okay? So this is where it kind of starts separating from a traditional Navier Stokes problem, because now you're gonna end up with two of these and two of these, okay? But let's just keep it going for now, you'll see. Partial u1, partial y is equal to negative rho gy sine theta. I just integrated it, right? Added a y plus c1. Then I integrate this one more time, so that becomes a y squared over 2 plus c1y plus c2. And two fluids, so same thing for the other one, okay? It's just, all that changes is the mu2, okay, right here. That dynamic viscosity is just different. That's what the problem's saying, right? Right, I mean, we said it here, right? Mu1 and mu2, separate viscosities, and it's open to the free surface, all that good stuff. So this is where we're at, okay? The only thing that's different between these, it's the mu2, the velocity 2, obviously, right? Different velocity profiles. And then the constants. C1 is now C3 here, and C4. So you have 4 constants, so you need 4 boundary conditions. So let's go ahead and do that, and let me kind of explain what's going on, okay? Before we kind of get overwhelmed. Remember, this is where it changes. So up to here was the same, but if you're doing 0H, 2H, this is where it's going to be a little different, okay? In this case, I chose the hardest one, right? Because it looks more complicated, negative H to H, okay? Just so maybe you want to try out the other origin. You'll get different C1, C2, C3, C4s, but at the end of the day, your answers should be the same for velocity profiles and all that good stuff. So you can kind of verify it. But in this case, my 4 boundary conditions for these problems, I chose one at the free surface, okay? That's right here, what you see here. I know at that location because air resistance is negligible, or like the problem said, right? So that means there is no shear stress between the fluid and the air, okay? So tau 1 is equal to 0. And I'll explain what this means in a second. Well, I just explained it, but I'll show you how we do that in a second. No slip condition at number 2, right? So these are the 1s and 2s. Like that's the ones I straight go to. Whenever you're stuck to like a surface, in this case at the bottom, you know velocity is 0. So boom, V2 is 0. And it's V2, right? Because this is fluid number 2, that's fluid number 1. So that's important. Tau 1, V2, okay? Fluid number 2, fluid number 1. Then the 3rd and 4th boundary condition, right? Because I need 4 of them. I said at the interface where the 2 fluids meet, the shear stress is the same and the velocity is the same too, number 3 and number 4. And what that means is like the particle of fluid 1 to fluid 2, though both of those particles are stuck together, okay? And that's why they share the same shear stress and velocity. And that's what I wrote here, right? Number 1, which is this one right here, at y is equal to h, right? At that top y, tau 1 is 0. So what that means is, from the equations from your book, that tau 1, it's xy, right? We're dealing with the x and y coordinate system. Mu times this is equal to 0, okay? So in this case, because we're dealing, let me move it like this. Because we're dealing with fluid number 1 up top, we're going to use mu1, and then we already determined that v was 0, remember? V is equal to 0. So that means partial v, partial x, take the derivative with respect to x of 0, we're just going to get 0. So this goes away. You're left with this term, partial u, partial y, of fluid 1. So mu1 times partial u1, partial y. And partial u1, partial y is this one. Okay? So that's what that means. So tau 1 is equal to 0. That means partial u over partial y is equal to 0. Then number 2, at y is equal to negative h, we're going to have velocity 2 is equal to 0. Okay, that's just no slip condition. We're good. At, let me move on. I'll just keep it for now, just in case. At y is equal to 0, so right at the interface between the 2 fluids, the shear stress is the same. Tau 1 is equal to tau 2. So what that means is the same logic that I did here. Partial u1 over partial y is equal to partial u3 over partial y. Okay? And then, what did I do? You're probably wondering why I didn't put the mu. Okay? The reason I did that is because let's just do tau 1 by itself, okay? Tau 1 is mu1 times this. We already determined that. I just said it, right? Well, divide mu to both sides, it just goes away. So you don't need it, okay? So these two are equal to each other. So you're going to set these 2 equations equal to each other for this one. Just FYI. And then for this one, y is equal to 0. You have velocities equal to each other. Now I can move this one here. Now, velocities are equal to each other. So I'm going to set these 2 equations equal to each other, right? u1 is equal to u2. I put v1, v2, but you get the idea. It is just velocity. I probably should have put u, just to not make it more confusing. But that's what that is, okay? So let's go to the next step. Right here. I don't want to show you the full paper just yet to not confuse you. But boundary condition number 1. The reason I chose that, I got to look at what's easier for me, okay? In this case, look, I want to do one of these. I try because I'm only dealing with one constant. If I go to this one, I'm going to have 2 constants. I'm not going to be able to do anything just yet. I like to see what I could do with this one. So partial u1 and partial u2. Well, this one tells me when y is equal to h, we set this equal to 0. So in other words, we're dealing with fluid number 1, the top fluid. So we're going to use this equation. And then for every y that we see, in this case just one of them, we're going to put h. And we're going to set the entire equation, partial u1 over partial y equals 0. So 0 equals negative rho gyh over mu1 sine theta plus c1. That's what I have here, okay? C1, I was able to solve for it, so just like that, boom, I'm good, okay? Now let's go to the next one. Boundary condition number 3. What does that one say? In this case, I already have C1, so I want to go to this one, okay? if I do this one, I can set these two equations equal to each other, right? These two. And I already found C1, so I already know all this. I know C1, I know this. I can find C3. So let's do that. Set the equations equal to each other, and for every y that you see, you plug in 0. So 0, right? So all this term goes to 0. And then 0, all this term goes to 0. So that means C1 is equal to C3 because I set the two equations equal to each other. So that's what I put here. C1 is equal to C3. C3 is the same as C1. Boom. That's just the same number, okay? Now let's keep going. Which one should we do next? In this case, if I do this one, boundary condition number 4, I'm going to set these two equal to each other, but I don't know C2 or C4. So I'm not going to do that one. I'm going to do number 2. I'm going to do boundary condition number 2 is for fluid number 2. So I'm going to use this equation, okay? I'm going to set, for every y that I see, I'm going to set it equal to negative h, and I'm going to set all that equal to 0, okay, because of that. And that's what I did here, okay? So when you do that, for every y that you see, plug in 0. No, I'm sorry, y equals negative h. So this is going to become h squared, right? Because you squared it, the negative goes away. So it's negative rho gh h squared over 2 mu 2 sine theta plus C3, but C3 we already found it. So I just plugged it in here and then just multiply it by y. But y is negative h. So you go from C3 times y. So just add a y here. And then that h is a negative h. So it's going to be a negative rho gh squared over mu 1 sine theta. And that's what I got here. And then plus C4. Now I can solve for C4. And C4 I calculated to be bracket 1 over 2 mu 2 plus 1 over mu 1 bracket rho gh squared sine theta. So just like that, I found C4, okay? Now, I'm gonna use the fourth boundary condition. I'm gonna set the two velocities equal to each other, and for every y that I see, I'm gonna plug in 0. So this goes away, that goes away, that goes away, and that goes away. And just like that, C2 is equal to C4. So these two are equal to each other, and these two are equal to each other. That's perfect. Now, you're probably wondering, like, how does that even make sense? Because I know I was when I did this problem. But let's kind of just keep walking through it, right? Let's see what we find. Now that I have all four constants, C1, C2, C3, C4, I could just plug them in, right? C1, C2 up here, and C3, C4 down here, and I'll get both velocity profiles. So for velocity profile number 1, I'm going to use this one. It's just negative rho g y squared over 2 mu 1. That's what I have right here, sine theta. Plus C1y, so C1's over here, rho gh, sine theta over mu 1 multiplied by y. I just throw y in there. Plus C2, which was all this. But in this case, I just threw it back in there because, look, I'm going to start adding terms. So rho gh squared sine theta over 2 mu 2 is that one right here, right? And then rho gh squared sine theta over mu 1 is this one. So just like that, I have this velocity profile for fluid number 1. And let me go ahead and simplify it. Just take a look at it for a second, but it's correct. Okay, I swear. All I did was just simplify it. The mu 1s, in this case, look, these are the three terms I could add together because they have the same dynamic viscosity. This one I can't, so this one just stayed the same. Okay, I multiplied both these sides times 2 to get the same common denominator, 2 mu 1. So that's 2 rho ghy, 2 rho gh squared. In this case, I had factored out rho g sine theta common to all of them. And then I factored out 2 mu 1. And then I end up with 2h squared, which is that one, plus 2hy, which is that one, then minus y squared, which is that one. So I found u1, okay? Now, for the same thing for velocity profile number 2. The only thing that changes, I just skipped it right here. The only thing that changes is that this one right here is a 2 mu 2. Everything else is the same, right? Because like 2 mu 2 plus C3, which is the same as C1, plus C4, which is the same as C2. So I was able to do that, and that is what you get. Just go ahead and trust me. Do it yourself if you don't believe me. Now that I have both velocity profiles, I could get my velocities anywhere, right? In this case, the problem says get velocity and shear stress at y is equal to 0 and y is equal to h. So let's stick with velocity. At y is equal to 0, we'll just plug in 0 for velocity, okay? These are my profiles up here, boom, boom. So y is equal to 0, that goes away. Y is equal to 0, that goes away. Okay, so this term stays, and this term 2h squared stays. So then I'll have 2h squared rho g sine theta. Okay, 2's cancel out. H squared rho g, that's what I have right here. H squared rho g sine theta over mu1. Let me put this down. That's for that term, plus h squared over 2 mu2 rho g sine theta. Now, because I'm finding velocity at y equals 0, they should be equal to each other, right? v1 and v2. And let's verify that. Yeah, look. At y is equal to 0, well, this goes away. So you have h squared rho g sine theta over mu1. That's what we have here. And then this one, y is equal to 0, so you just have h squared over 2 rho g sine theta over mu2. And boom. Notice how they're equal to each other. So that means it's correct. You could, actually I didn't find velocity at y is equal to h, but it's the same thing, right? In this case, I want velocity at y equals h. So because I only want it at y equals h, I only focus on u1, okay? The u1y. Plug in h here and see what you get, and that's your answer. It's just algebra at that point. Shear stress, and let's go ahead and get it at the interface. What is that shear stress value when the two fluids meet? Well, that's just this, look. Remember shear stress, we determined it to be tau is equal to mu times delta u over delta y. Well, what's delta u over delta y is this? These two, right? So in this case, I already have C1. So do the math, right? Plug in this. You're going to have, I'll just do it with you guys, my bad. So C1's right here, okay? And I care about C1 because that's what this term has it here, okay? So it's negative rho g y over mu1 sine theta plus C1. C1 is rho g h sine theta over mu1. Now, this one's over mu1, so this C1 is over mu1, and this one's over mu1. But guess what? So is the shear stress. Mu1, remember? So they cancel out. Mu1, these two on the denominator, multiply it. Because this term, remember, this term right here that I'm circling, gets multiplied to a mu1. So this goes away, and then the mu1 that was from C1 goes away, okay? So just like that, you're left with this right here. This is just me simplifying it. So you'll have the mu1 went away. So you'll have rho gy a negative plus a rho gh. So it's h minus y, and then everything gets factored out. Rho g sine theta over mu1. Mu1's canceled out. That's what I have here. And then that's your shear stress, okay? So h minus y times rho g sine theta. That's your shear stress. Now, we want it at y is equal to 0. So we plug in y is equal to 0. It's just rho gh sine theta. Boom. And you'll see it's the same case for tau 2 as I did it here. So feel free to just take your time with them, do them. But that is how you do this problem for an inclined Navier Stokes problem for two fluids that have different dynamic viscosities. So I hope that helped.